So here we are, I think. Yeah, okay. So let me repeat what I just said. So I realized during my first chapter that I have much too much material. I will not make it through the end, but I don't want to rush. And I would like to again encourage you really to interrupt me and ask questions, such as the good questions I had already. And if you like at the end or so that we should have another lecture summit later at some later point or so, I'll be ready to do that also. You can think about this. Okay, so as you have seen, we have seen that we need to treat microscopic particles in terms of quantum particles. And the question is now for controlling. This is the subject of my lecture. We need to, what I call taming them. In other words, we need to make sure we know where they are, how they behave, what they do, and so on. So let's go into this. And yeah, here I am. So this is actually a picture. I sent it to you earlier. It's 4 atoms, and you need to be able to see them for a sufficiently long time, especially, for instance, if now we want to, if we want to, for instance, make controlled interactions with them, implementing, for instance, a quantum gate. If you use your atoms as qubits, would mean controlled interaction in terms of time, location, and so on, and internal states of these atoms. All right, so yeah, I like to a little bit compare it to, in Europe, we have these flea circuses. I'm sure you have something similar or so, also in Ghana or so. And I mean, with big animals, you can see what happens, but with little animals, they're very fast. Yeah, and so you have to be very careful of how to control them. And atoms are even smaller, and so you have to do even more in order to control them and so on. So what do we do for atoms? And from my perspective, a crucial experiment was carried out in 1980. This is what you see down here, 1980. And this was the group. Hans Dehmelt was among them, Peter Toschek and Werner Neuhauser. And so the initial taming of quantum particles was trapping ions. An ion is simply an atom with a charge. Yeah, so you typically it's a negative ion. Typically it's a positive ion where you have taken one of the atomic electrons away. You can also trap negative ions, but they are much harder to treat. So positive ions. So of course, what you can do is you can exert very strong forces. The charge of an ion is like a handle that you can use to grab this particle. And with electric fields, you can do that. And of course, what you would like to do is you would like to fix a particle at a certain location in space. So let's look only at the left part of this picture here. And now, if we use simply negative and positive charges, then a positively charged electron or atom will be attracted towards the negative electrode or so. Yeah. But there is no point. It will always run into this electrode. This is not what you want. You want to keep it off the electrode. Your system of electrodes should act like a container without walls. By the way, I think somebody is making some noise, and it may be nice if you switch off your microphone in order to get rid of this noise. Then positively charged atom would be attracted here. Now, there is a 0 point in this arrangement. If you have a capacitor, you know there's only electric field lines running from the negative to the positive side of the capacitor. It's all homogeneous, and the electrons and the charged particles will all end up in the electrode. This is not what you want. So this is a quadrupole, what we call a quadrupole arrangement. And it's only 2D here, but it can be extended to 3D by simply making this a ring electrode, as you will see in the next slide or so. Yeah. And there's a 0 point here, but this 0 point is unstable. because as soon as a charged particle from the 0 point would veer off a little bit, it would immediately feel an electric field and then again rush, if positively charged, into the negative electrode. Then in 1948, 1949, Wolfgang Paul and his collaborators invented the so-called Paul or radio frequency trap. So what they said, okay, what we do is we keep an oscillatory field between the electrodes. So this quadrupole arrangement is now continuously changed from positive to negative to positive to negative. And in a very simplified picture, what happens then if the if the atom is attracted, the positive atom is attracted by the negative charge, by the way, as it wants to arrive here, it's positively charged here, which repels the atom, and now the atom tries to move to the negative pole again. And again, if it comes too close, it's again positively charged, and then keeps going on this track. So you can imagine that by doing this dynamic electromagnetic field, we can indeed trap or confine a charged particle. A mechanical analog is shown here. So the mechanical analog of a quadrupole here is a saddle point potential. So if you put a excuse me, if you put a particle here at the perfect saddle point, then the particle will soon roll off to the sides, yeah, because it's an unstable equilibrium here. It will not go here, but it will roll off to the other side from the saddle point. This is what corresponds mechanically to the electric quadrupole. But now imagine if you set this saddle point into motion, then the particle will feel an average potential, and this average potential will indeed create a restoring force towards the saddle point itself. So this is what you want, yeah? And initially, Hans Demel did this with electrons. Again, electrons were easy to use, and also electrons, yeah, I will say a few words about this. And then other people started to trap also positive ions. And one of the first ions to be trapped was barium. Now, why barium? Barium is in the second column of the periodic table. It's simply a very convenient one. It looks like an alkali atoms, which are other electrons, and they are like guinea pigs. Yeah, they're like really playing the atoms you want to play with in atomic physics and quantum optics, because they are very convenient in terms of handling them also. And he called this a monoion oscillator. So in barium plus, in contrast to electrons, barium plus is like alkali atom. So like the best known alkali atom is sodium, and sodium makes the yellow light of the Fraunhofer lines, or also in street lighting and so on. If you find yellow light, it's all sodium atoms fluorescing there. And so the barium ion can be illuminated with green laser light, and then it sends off fluorescence light. And this is what is shown here. This is, you will understand this in a moment in a better picture. This is really the ring electrode. Imagine that this is a ring electrode, and then what you see here, this really is the ring, yeah? You really see the ring around. This is the end cap, which is from the top and the bottom. And in the center, what you find is a fluorescing barium ion. And so this is a single barium ion. You will see in a moment how we can also detect that this is a single particle and not many particles or so, yeah? All right, so, and from my point of view, this really changed the world, because in my point of view, this experiment really initiated our today control of the world of quantum particles. So, and this was in 1980, you see it's now about 45 years ago. A similar experiment was carried out in Dave Wineland's laboratory in Boulder in the United States. And this one was in Heidelberg. But these two experiments, from my point of view, really initiated this control of quantum particles, which today we are taking to the point where we could even build quantum computers or so. All right, so let us go on. Here you see the same picture again. And so this is only the stray light. The interest, actually, one problem is this: one atom doesn't make a very strong light source, but you have to detect this very strong light source. So you have to take a lot of care to discriminate this weak light source
from the environment. And you see some weak stray light, in this case, from this ring electrode. So this barium ion is in the center of this ring electrode, and there, and this is the ring electrode. And what you see here, this is stray light from the ring electrode, and up here you see the so-called end caps, and they also cause some stray light. But the signal to noise ratio is good enough to really identify this barium ion here. Now, this is more modern variants of this. We don't have to use this complicated structure. Actually, these are hyperbolic surfaces, so they are not so easy to machine. Today it's all better also, but we have learned today to just use much simpler devices to create very similar electric field arrangement. That's the only thing that counts, yeah? What is the electric field arrangement in the vicinity of the particle, not the details of how you generate them. Today we have simpler ways of doing this. So this is about electrons and ions, and in this slide I would like to show you the wealth of platforms which today we are using for working with these kinds of quantum particles. The next which I will talk a bit more about is neutral atoms. And neutral atoms, this is a picture of two neutral atoms, cesium atoms, actually from my lab. And you can see they are actually trapped in a perfect array. And this perfect array of laser beams, this is a standing wave of laser beams in 2 dimensions. So one laser beam is traveling in this direction, another one in this direction, and in fact a third one in the third direction. And then you have a perfect square lattice of intensities. And the atoms in this case are actually attracted to the high intensity points of this lattice. So the high intensities, this is where you have these little mountains or these little peaks here. And then if we have an atom trapped in any of these peaks, and here there's 2 atoms in 2 adjacent peaks, then you see that they are fluorescing nicely if you do everything correctly. And the microscope, I will say a few words about this, the microscope even has good enough resolution in order to really identify the location, the individual location. And this is very important again also. We want to be able to identify the location where the atom really is. And so the separation between these dots is actually roughly half a micrometer or 1/2 of a thousandth of a millimeter. And our microscope is good enough to resolve this, which is not trivial. You may, and this is of course under really challenging conditions. I will show you this in a moment. All right, and then a very active and recent research field is also molecules, to work with molecules in this case. In the next slide, I think I will collect a few arguments. What kind of properties do we actually need for a good quantum particle or so? Molecules are difficult. Why? Atoms are the prime choice for quantum particles because they are perfect, atoms and ions, because they are perfect quantum objects. They have a very clean structure of their quantum states, and the number of degrees is not too small. In physics, and especially in this field, in the end, we will need to reduce the number of degrees of freedom to the smallest possible number of degrees of freedom possible. And molecules, because they are at least 2 atoms or so, they can vibrate, they can rotate. And these are low energy excitations. So they are a lot more difficult to treat. And but it's a very attractive field also because they have some interesting properties one could use for quantum information processing. But as I said, I think over the past 30 years, electrons and neutral atoms in this part have been the front runners. Molecules are a more recent achievement, but they have some promises of good properties for future quantum information processing. Now, as I mentioned earlier, when we want to work with quantum particles, we need to make them slow. Yeah, remember from the Broglie wavelengths, h is the quantity which defines the microscopic world, and divided by m times v. Now, for atoms, they have within a factor of 100, they all have the same mass, the proton times their atom number mass or so. And so they are fairly heavy. So we need to make them very small in order to get long to get low wavelengths and so on in the wave picture image or so. So in other words, what is absolutely necessary for these particles is that we can laser cool them. Laser cooling is absolutely required because otherwise in a thermal or in a gaseous environment, even if we could trap them, there will be at very high velocities. So for instance, in air at the room temperature, or so at 300 Kelvin, the molecules in the air have typical velocities of order 300 to 500 meters per second. And this is much too fast to do any experiment. So we need to slow them down. And the big invention to do this slowing down in the gaseous phase was laser cooling in the 1970s, 80s, and early 90s, which led to all this development. Okay, well, the big disadvantage of electrons, ions, atoms, and molecules is they are usually, when you start in the gas phase, and they run away. So you have to do a lot of effort, as I just mentioned, in order to make them localized at a certain position. So it is, of course, a very nice idea to do away with this. And one of the first ideas to use other instruments was to use color centers. Here's a color center shown. This is what is so-called nitrogen vacancy in diamond. So the green dots here are carbon atoms, and they have four they have 4 valence electrons and so on. Yeah, and nitrogen has only 3 valence electrons, and in order to compensate for this, in order to make the overall charge neutral or so, there has to be a vacancy in this crystal. Yeah, so the nitrogen atom and the vacancy, and this vacancy acts as a trap for electrons. And these systems here look like atoms. They're almost like atoms. They have very discrete levels. They are clearly identified, and obviously they don't run away. Yeah, you will see in a moment, or I will comment in a moment, that they have other problems, because the good thing here is we really have an atom, and this is well separated from this atom. It's about how much is it? It's about a micrometer or half a micrometer, as I said. Yeah, here it's a few angstrom, and there's a very strong interaction between the atoms here. They vibrate because they are not at 0 temperature, and so unfortunately, to some extent, there's other advantages, but to the disadvantage of these color centers, they vibrate, and so this is the price you have to pay. So whatever you do to work with quantum particles, here you have to do a lot of effort to make them slow, to trap them, and so on. Here you have it's no effort, it's effortless to trap them, they just sit there, but you have to do a lot of effort in order to identify the states and to isolate the properties that you want to work with. Another center in this direction is a so-called quantum dot. This is a so-called quantum dot cavity. I will show this in a moment in a bit more detail. This is about 2.5 micron wide. It's a material particle made from gallium arsenide in a mixture with indium arsenide. And the third one is the so-called transmon qubits. This is superconducting circuits. There's 4 of them here in this case. This is from IBM. It's already 8 years old. Now IBM in these days is integrated about a few hundred or even 1,000 of these qubits on a single chip. And again, we have dimensions here. This is a few microns or so, and this acts in the microwave domain. I don't want to talk about this, but as I said, these are the platforms which are the present platforms which we use to construct also quantum computers. From my personal point of view, the transmon qubits, the electrons, and the neutral atoms are the front runners in the game and the race for who is going to establish the most effective quantum computer system. Of course, then not with single quantum particles, with many and controlled interactions or so, yeah? But this is the future. And so in these days, we call this platforms. And this group of systems here is also called artificial atoms. And let me comment for a moment also on the question, what makes an artificial atom relevant? Besides besides not running away from your experiments as the ones on the left side do. So here I show two specific artificial atoms. Yeah. Here, this is again the color center. So this is symbolizing diamond, and this is this thing which looks like an atom, but it's sitting in here. So it's atoms in matrices. They do not run away. It's the pro. They have long storage time, or they actually sit there forever. But the contra is a so-called, what you need is a so-called zero phonon line. So when you emit light from an atomic transition or so, in an atom it's clear. In an atom, the Bohr quantization rule, or the quantization rule, simply is the energy, as we saw on the stamp for Max Planck, is simply h times the nu, the difference, the energy difference, or the difference frequency between the two quantum states. This is not entirely true. It can happen here also, but there is a so-called phonon sidebands. So when a nitrogen vacancy makes a transition from an excited state to a lower state, then it may not only excite the photon, but also in addition a phonon into the crystal, because it is coupled by the exchange forces, by the binding forces to the crystal environment. So only a fraction of the emitted photons goes into the so-called zero phonon line, where no phonon is emitted. And since at room temperature only a few percent of these phonons are emitted into this so-called zero phonon line, their use for quantum computing to this day is questionable or so. On the other side, this low efficiency in this respect does not impair their use as very good and successful quantum sensors for magnetic fields and many other applications. On the right side, what you see is a quantum dot. And so here actually what you see is an electron micrograph of a cut through of the quantum dot. So this is indium gallium arsenide's material around here, and this is a somewhat different composition. And the different composition of indium and aluminium excuse me, indium, aluminum, gallium arsenide means that there is a potential hole. It's almost like the particle in a box example that you calculate in elementary quantum physics. Yeah. So there is an electron that is sitting here, and there's also at the same time a hole in the valence band. So in the conduction band, you have an electron sitting here. In a potential trap on the valence band, you have a hole, and they can recombine and emit light. And this is what we call a quantum dot. Yeah. So it's a semiconductor thing. And they have very nice properties in terms of generation of photons. This can be done at the highest possible rates of all quantum particles. This is in the gigahertz region. So I don't go into this into any big detail or so, but if you're looking for single photon sources, then quantum dots are certainly perhaps the best bet. At least if you just look for the rate of photon generation. They can rate photons at the rate of gigahertz or so. Then I will show you an experiment with photons, but only in the third part, so maybe not today. If you do it properly, then the photons emitted from this structure here are even emitted along almost a single direction. So you can catch all them and use all of them, and you don't lose many of them. Yeah. So the trouble is that if we want to go for quantum information processing and for real quantum dots and not only a single atom, if you want, so yes, it is a very tiny and small particle, but the quantum properties in the end will only show up when we start how do I say, using quantum superposition states. Yeah. With these quantum dot systems in the recent past, very good progress has achieved. So now people in Basel and my colleagues at the University of Bochum are able to make quantum dots. If you use two quantum dots, then their individual photons interfere almost perfectly. I mentioned at the electron interference experiment that we need to
make virtual images of a single source of these electrons in order to make them interfere. Now here we are approaching a much better situation. We can use two independent light sources, quantum dot light sources, and their photons will nicely interfere, which is really a big achievement in terms of technology and quantum technology. All right, so let me comment a bit more on what makes a good, so to say, quantum particle from the point of view of an experimenter and for practical purposes, because we want quantum technology to be real and not just on paper. So, as I mentioned already, the localization is very important. I showed you that we can use trapping devices or matrices for doing that. They also need to be detectable. So for the barium ion and for the atoms, I showed you is all fluorescence. We use a so-called resonance line, which is able to emit about 1 photon per, let's say, 1 to 10 nanoseconds or so. So a total of, let's say, 10 to the 8 photons per second. This is good for experimenters because even if they only are able to catch 1% of them, they still have enough signal to discriminate this atom from anything else in the environment. By the way, with electrons, obviously you cannot use fluorescence. So in that case, it was the currents. An electron moving up and down between electrodes induces a current in these electrodes. And this current was used to detect the electron, which is a really very high class electronic device to really be able to detect this with very low noise devices. And then in the end, this is not sufficient even. We need what I call clean quantum states. A clean quantum state is shown here in the lower left. Yeah, a clean quantum state in the ideal case consists of no more than 2 quantum states. This is what makes atoms so preferable, or ions. They are the same in this case. And since we want to control them, as you will see in a little while also, we need one auxiliary state which is necessary to control these quantum devices. So that's all. And obviously, as I mentioned, molecules, for instance, are having difficulties to obey this kind of situation. Yeah, and so this is a 2-level system. And today we call all these 2-level systems now qubits. The word qubit existed since the 1980s or so, I think, but it was not around really in the community until the early 2000s. So what we used to call 2-level systems is now called qubits, a bit more modernistic or so. And of course, what is important here is that qubits have to be described by the Poincaré sphere. I will come back to this also a bit later or so. So a classical bit is just having a 1 and a 0, these 2 numbers, these 2 classical numbers, and this amounts to the North Pole or the South Pole orientation of the system. And indeed, for a spin 1/2 system obeys this. So if you just look at spin 1/2, then if it's in the up state, it's a classical 1, and if it's in the spin down state, it's a classical 0. However you assign the zeros and 1. But in the quantum world, we can also generate superpositions. And then we have the full-scale quantum bit available, and we need the so-called Poincaré sphere or Bloch sphere to describe the quantum dynamics of such systems. All right, let me compare ions versus neutral atoms to give you a little idea of the differences. Yeah. What are the properties of ions? Well, ions have a potential, which is the charge times the potential. And so the charge is an electron, and the potential is order of 1 volt. So the potential energies are on the order of 1 electron volt. This is extremely deep. If you have 1 electron volt, if you would calculate this, divide this by the Boltzmann constant, you find out this is 10,000 K. Huge number above the room temperature. So with these electric potentials, setting them in this dynamic rotation, as I showed you for the power trap, it's relatively easy to trap ions. They are not in the lower state, they are thermal ensemble. You still need to cool them down by laser cooling methods to the lowest quantum states, but it's easy to have them at least in the trap. They can be trapped for days or even in the record things, they even have been trapped for a month or so. Yeah. Another nice thing about ions is that the external degree of freedom, that's the trapping forces, Q times the gradient of the potential, are independent or almost independent of the internal degrees of freedom. So you can use the not macroscopy, the motional degree of freedom. The ion moves as a whole object or so, and the internal degree of freedom completely orthogonal or independently of each other. Yeah, and a disadvantage of the ions is that as soon as I mentioned already, in the end, we are not only interested in understanding all the properties of single particles, we want to control one particle and then bring it into interaction, controlled interaction with other particles. And the ion-ion coupling is very strong, which has some good parts about it, but also some very bad parts or very, very disadvantageous parts about it. So when you use more than one ion, you have to always deal with this ion-ion coupling, and then it's a whole different system than a single ion. In contrast to ions, this is very good about atoms. If you use a lot of atoms, the interaction of atoms, if they are not too close to each other, is very weak. So that for many purposes, you can, at least in the first case, in the first approximation, completely neglect them. So the potential we can have for an atom is the induced dipole moment times the electric field. This is the potential energy we can ascribe to a neutral atom. So we induce by an electric field an electric dipole moment times the electric field. We will see this in a moment. But then we can calculate what is the electric dipole moment. Actually, what is the scale of an electric dipole moment of an atom? That's also straightforward. It's the charge of an electron times the size of an electron, EA0, the Bohr radius, and so on. And then you can again think of what is a typical electric field. I can establish with laser lasers. Then you find out, look at this difference. Here it is 1 eV. Here we have 1 micro eV. So 10 to the 6 times or 10 to the 7 times smaller potentials, which means that we need to have effective temperatures of 1 millikelvin or below before we can start trapping atoms. This is why atom trapping became available only around 1990 at all or so. And then, because the atoms are so trapped in such shallow devices, they can only be trapped for minutes. Now, with very good vacuum devices, you can trap them for, let's say, an hour or so, but it's far away from the time you can use for trapping ions. Also, since an induced dipole moment acts on the internal degrees of freedom, the external, the motional degree of freedom, and the internal degree of freedom are intertwined. So it's not as easy in this case. Okay, so even though both have their good justification and their strong advantages or disadvantages to be used as quantum objects. So as I said, we need to establish laser cooling. Now a few words on laser cooling. Here it is. So if we irradiate an atom with laser beams from the left side and from the right side, then what happens is that the atom is excited by these laser beams and it re-radiates, it fluoresces. This is what we call fluorescence. Now, the laser beams is unidirectional here in this simplified picture and unified in this picture in this direction here. And the atoms therefore receive the absorption from a clear direction. So from this direction or from this direction. Okay. In fluorescence, however, the fluorescence occurs in all directions. And since this is a stochastic process, the effective absorption of photons from this side or this side causes a decelerating force if we choose the exciting laser frequency a little bit below the resonant frequency, because if you choose, we call this retty tuning, so only when the atom moves toward this laser it has the right, because of the Doppler effect, it has the right resonant energy and will absorb energy. And because of the recoil, if the atom absorbs a photon from this side, it will experience a recoil. So it will experience a force to the right, and vice versa on the left side. And so it will exert, there will be forces, and on the other side, this will also exert a force, but this force will always be in stochastic or in random directions. This means on average, there's a small force on emission and a clear force on absorption. So this means indeed that we do have a decelerating force. Yeah, and this is a decelerating force, and we can actually draw a picture from so we have two resonance lines here, and because of the Doppler effect for the force from the left and the right, they are slightly shifted against each other. And then if you look at the two combined forces, then you have this kind of a profile. And in this case, this is the effective force that occurs due to this process here. And in this case here, if you choose the tuning a little bit to the right, you see here that there is a linear force. This is as a function of the tuning, but this is the velocity. Yeah, so this is also the velocity. The tuning due to the Doppler effect, which is linear here, is the same as the velocity. And so this means we have a force which is proportional to the velocity, or negatively proportional to velocity, and that is the damping force. This means that we really achieve cooling with this laser cooling. Yeah, so this cooling is very important. It's not only slowing, but it's cooling. For the experts, this means that the phase space volume is reduced. So, and well, then we can ask questions. So how would the temperature in the end be for the cooling force? And we can make a simple dimensional argument. KT, which is the energy of an ensemble. I neglect all prefactors here, like 1/2 or 3/2. The temperature is proportional to this energy, which is the typical width of the resonance line and of the dissipative properties of the atom. And then you find the Doppler limit. So from this simple formula, you can calculate a temperature which is indeed very small. This is the h bar gamma here. And you find something on the order of millikelvin or even below microkelvin or so. The interesting thing which was found in the 1980s was it works even better. There came the so-called subdoppler cooling, which I have no time to go into this here. And the subdoppler cooling earned the Nobel Prize for Claude Cohn-Tanucci from France, from École Normale, and for Bill Phillips and Stephen Chu from the United States. So, and the most important instrument in this case was realized in 1987 by Jean Delabarre already in France. And so the only problem, so here you see now that there are laser beams causing or offering laser cooling to atoms, in this case from all sides. The only problem is that that if you use only laser beams, there is no 0 point again. And but it was found, and this was the idea by Jean Delabarre, that if you put on a slight magnetic field, I don't want to go into the details here, then indeed there's something like a 0 point here where the atoms want to go to. And this is called the magneto-optical trap, which is the workhorse of all cold atoms experiment around the world. I'm sure there are hundreds and thousands of magneto-optical traps. Even in Bonn, for instance, we operate magneto-optical traps in our practical training for the students already, because it is so important. And this was really disruptive, because all of a sudden you could use few and many atoms. Now there's one unfortunate thing about this. You keep scattering atoms in order to make them collect and locate at this point here. And for quantum processes, this is something you do not want, because you continuously destroy any quantum coherence. You cannot have any quantum coherence by using scattering forces, because so you excite an atom, then it decays in a stochastic, in a random way, and this
would immediately, more or less immediately, ruin any quantum coherence you want to induce. So we have to have other systems. And oh yeah, by the way, one thing we find, before I go on, now this is a very nice way to show that we really work with neutral particles. This is from my own lab back in the early 1990s, already 1995. So if you do everything properly, this is the background level. So you really have to shield all stray light. Remember the stray light from the ring electrodes for the atom, for the ion. But then when an atom comes in, is trapped randomly in here, then you see here, the level of fluorescence rises immediately and stepwise. And a second one is coming in here. And a third one is coming in here, yeah? And again, here, you see it also. And you see some interesting dynamics immediately already here. Sometimes you see two atoms at a time leaving the trap. This means that there is an interaction between these two atoms, because this can only happen if the two atoms do interact with each other, and then they leave the trap in pairs, yeah? And so, as you see here, this dynamics is already allowing you to investigate physics. Also, you see here the trapping time, which is of order of minutes here. Yeah, so the atoms are sometimes lost, and then you lose them after, let's say, the order of minutes. This trapping time is only a question how good your vacuum is, because even in the vacuum, you have, of course, then atoms which once in a while kick this atom at hot temperature with high kinetic energy, and then it's lost from your trap. Okay, so for neutral atoms, the solution out of this is to use optical dipole traps for neutral atoms. And the optical dipole traps is also now called optical tweezers, and it's a very big thing now for building quantum computers, is a laser beam which is focused to a very narrow spot. Yeah, and we need a magneto-optical trap to do pre-cooling, and then we switch on. In our case, it was a standing wave laser field. So what you see here is a laser propagating in this direction and in this direction, and it makes a standing wave field as an electromagnetic wave. And so if you focus this, then the square cross-section is maybe on the order of 10 micrometers, and the separation, similar to the two-dimensional optical lattice I showed you, is on the order of half a micron or 1 micron or so. And so in the depending on how you make it, but the most frequently used way is to use these intensity maxima as potential wells. Yeah, so you see here, this potential maximum compares to a potential well, and this one corresponds to the next one, on the other side to the next one. The separation is 500 nanometers or half a micron, and as you see here, it looks like a harmonic oscillator. It looks like a harmonic potential, and to quite a good degree, it actually is a harmonic potential. So, and then what we have is we want to calculate now the depth of this potential, and we assign a temperature by taking the energy in joule divided by the Boltzmann constant. And so the dipole moment times the maximum field strength is simply E times the Bohr radius times the maximum field strength you can achieve. And well, this maximum field strength depends on the laser power, on the cross-section that you have here. This is the total laser power, yeah? It's the intensity which is propagating. This is the maximum electric field strength, and this is the cross-section of the field. And you find that at 1 watt of intensity, which is the typical laser power available in the laboratory, you have a depth of 1 millikelvin, no more. But because we do have now this extremely efficient pre-cooling stage by the magneto-optical trap, this one here, it is sufficient to trap our atomic particles. And so from my own laboratory here, this is a picture of what happens then. Here you see a laser beam, and we can do a special thing. This is what we call a traveling wave, or a transport velocity band, a transport belt, an atomic transport belt or so. And so if we detune the laser frequency of one of the lasers a little bit relative to the other laser beam, then this transverse
then the standing wave will be set in motion. It will be a traveling wave, yeah, then. And if we have trapped the atoms in there, the atoms will simply follow and walk along with the traveling wave beam. And in 2003, this was our first experiment, and one of our first experiments. And here you see 3 traveling atoms in such a laser beam. It's a little bit faster. It's a little bit faster than real time or so. Here you see the scale, and you see also that we have about a minute available. And after some time, due to collisions with background gas in the vacuum, which is not perfect, you see that we lose the atoms. So in this case, after roughly 2 minutes or so, we have lost all of them. Today, our vacuum is actually better, and we can keep it 10 times longer or so. But as you see, we can really see atoms moving along. And for a long time, this was very good. And let me make also a technical remark here. This was our first camera which was able to detect single photons or so. And so this was an immediate application. And it shows also in a very nice way how the progress in experiments is intimately coupled to the progress we have in our technological equipment. Yeah. Okay, so I can see, oh yeah, then we were able to sort these atoms here. You see regular patterns. This was an early one. Today we can do it actually better. We were able to make nice, beautiful arrangements of atoms at that time, which earned us a lot of credit in the community and so on. And maybe the last thing I show you for today is we need a really good microscope. Yeah, I told you that the question of technology is absolutely important. And here you see a microscope. And the essential part, the most important part of the microscope is the objective. And here's the objective. And so because we are in vacuum, we cannot work as you do in biology. In biology, you make very flat samples and put them immediately on top of the microscope, maybe with some liquid in some index matching liquid in between. So in our case, we couldn't do this. So we had to stay a little bit off here at the level of about 150 micrometer, so a tenth of a millimeter or so, in order to see our atoms. And then, however, the first surface is really flat. And this is really good because you have a very high opening angle. And I hope you remember that the numerical aperture of an atom, which determines your resolution, is proportional to the opening angle that you have here. But it's not only the opening angle, it's also the amount of fluorescence you can catch from an atom. As I told you, on fluorescence, the atoms emit their light into all space. It goes everywhere, into the full 4 pi solid sphere, solid angle or so, yeah? So the larger you can make this entrance phase here, the more light you are catching from your atom. And of course, this is desperately needed signal from your particles. And so we have this here. And then in our case, this microscope objective is only built from a second lens. And this is now a aspheric lens. And today we can make very nice aspheric lenses. And so with very high quality. And then the final part is to make this objective, to mount this objective, yeah. And because of these very precise, highly precise things, it is very essential to make a good mounting. And so we had to have this holder here, and the tolerances of this holder, which this is roughly, let's say, 3 centimeters across or so, the tolerances of the dimensions of the opening and of the relative position had to be machined to the level of a few microns also. But this is possible in these days. And then we could make a very nice point spread functions. In case you are an expert in microscope objectives, you know that this is the essential figure, or the Strahl ratio. And anyway, so as you see, again, the progress in the experiment really depends on state-of-the-art equipment. And my doctoral student, Stefan Bakane, did a great job in all this. And here again, with this microscope objective, this was essential to see. You saw this picture earlier here in this case. Okay, I think I want to, and I need to stop at this point. Maybe I give you as a last example my final slide of my lecture. And so I have to come back just a moment, please. So here, this is my final, I want to show my final slide. Can you show my final? Just a second. Okay, my final slide here. I think I've only been showing you the first steps of how to get into controlling quantum particles. And what is really needed is a passion for precision. And one of my heroes in physics, Daniel Kleppner from the United States, expressed this in an article already in 1989 in Physics Today, that you really need the handicraft people to do really good job on this, and only then we will, what is in the end really interesting, be able to create superpositions of quantum particles in terms of quantum states. So with this, I would like to thank you for your attention, and I hope that at least you have obtained some initial ideas of what controlling quantum particle means in the real world of a laboratory. Thank you very much. And again, if you have any questions or so, come forward, or also send me an email if you want to know something. I'll be happy to answer your emails also.
Okay, thank you, Prof. Please, I want to find out these activities in the lab. Do you have video clips on it so that we can at least have a gist of how the whole activity goes about in the lab? Maybe it's on the YouTube or...
Yeah. I must confess, I'm afraid, not offhand, but I will look. Maybe not exactly from my lab, but from other labs. My lab has been closed, but I have a successor, and we may have. I will take your question and look into this in order to find out what we can do. Please, it would be nice if you would send me an email to remind me, and so that if I find something, I can directly contact you.
Okay, thank you very much.
More questions or remarks also. I understand this recording will also be available for you if you want to see something again also.
Please, can you hear me?
Yeah, I can hear you, yes?
Okay, all right. Thank you very much. Please, will it be possible for us to get the slides, and so that we can go through once again? Or
sure. Yes, I can
like
make absolutely. I can make the slides available directly for you. I also have an article. I've written together with my colleague Andrea Alberti a little article on single neutral atom trapping, which I can make available also.
Thank you very much. That would be so great. Thank you.
Yeah, and again, please send me emails so that I don't forget and that I know what you really want.
Okay, sir. Thanks.
Okay. Any other question?
Prof, I want to ask in the magnetic optical trapping, like the magneto trapping.
Yes.
Is it that the trapping of the particle, is it done by the laser beam or the magnet, the magnetic part?
Yeah. Okay. Yeah, I think I showed you. Let me go back to these. Okay, I have to. Let me see. There's so many slides in between. I have to rush over here for one moment. So let me. Maybe you remember this slide here or so. So these is a one-dimensionally simplified picture. So you have laser beams acting on the particle, on an atom typically, yeah? And so there is a force from this side and from this side, and the combination of these two forces makes a linear force along this direction. Okay?
Please, we can't see your screen.
Okay. Oh, sorry. Then I have to. Okay, I'm sorry. All right. So now you can see the screen again.
Yeah, yes, please, you can see it.
Okay,
Yes,
then.
we can see it.
Okay, then let me. Oops. Let me. Something happened. Okay, I have lost my my online. But you see my mouse also here. So this here, actually, I can even. So this is creating a force, and this is also creating a force. Yeah, and these forces do act like a friction force. So it slows down this particle here. On the other side, this will be a random force, and a random force causes a diffusive motion. It's a random motion, so the particle will always jitter around somewhat. Yeah, and since here, whether this happens here in the place or here doesn't matter. The particle doesn't know. Yeah, there's always two laser beams coming in from the left and from the right, and it always keeps scattering. So it would be very slow, but it would jitter around and randomly move around. And of course, so in order to make it in 3 dimensions, you would have to add another pair of lasers here and also in and out of the plane. And now let me go to the next slide. So now we go to the next slide. And now okay, sorry for this scribbles here. So now what we add is a pair of magnetic traps. And as you see, this is not Helmholtz coils. Helmholtz coils have 2 currents in these coils acting in the same direction, and they create a homogeneous field in this position. This is just the opposite. It's anti-Helmholtz coil. Here it's right-handed and here it's left-handed. This means there's a 0 point here of the magnetic field. And this, in a very loose way of saying it, it causes the atom to find out where is there a point of slowest restoring force. Yeah. So the atoms will move to this position here. Okay. So does it reasonably answer the question you had?
Yes.
So the answer to the question is actually the trapping forces are generated by the laser beams, but the magnetic fields tells the atom where it experiences the best balance of these forces from left to right. So when it moves off from here due to the magnetic field, there is a magnetic field here, there, and there in opposite directions. Here it feels a force here it feels a force here, but here it doesn't feel any effective force due to the arrangement of the magnetic coils. So the magnetic coils only modify the action of the laser cooling fields and the trapping fields. Okay?
Yes, yes.
All right. Any other question?
Yeah, hello, Prof.
Yeah, go ahead.
Hello. Yes, with the double slit experiment.
Is the question whether the outcome of the
outcome, yes, the outcome of the experiment that you were explaining.
The outcome of the experiment, the variance of the double slit experiment with the electrons, or also with the Mach-Zehnder experiment, is formally, in fact, you use the same mathematics, and in the experiment it's confirmed, it's identical to using light fields. I mean, okay, so I read your question from the chat. I mean, in the experiment, there were different observations. My question is, are they type of spectral lines? I'm not entirely sure what you mean by that, really. But okay, let me go to the experiment. Yeah, there's a question. I will try to answer this question. So, number 1, this is the first experiment. So this was the kind of double slit experiment. Yeah, it's a variant, what I say. So you could just replace this by 2 slits here, and it's fully equivalent to a double slit experiment. I explained all this here. Yeah, And now let me try to guess what you mean by spectral lines. If you look at a double slit experiment by using a laser with a single color, yeah, for instance, a green laser. Actually, everybody, if you have laser pointers, many people around the world have laser pointers. And if you use a laser pointer, you can easily do this experiment at your home, and you can make a simple with paper or whatever double slit, and then you will find nicely these dark and bright lines. If you use white light, which has many colors, then of course it will be very difficult to observe this, because then it's a superposition of all colors. The spacing between between the dark and the bright lines depends on the wavelengths. And so if you have a single wavelength laser, such as a laser pointer, it's straightforward and easy to find this. Yeah. And the white light makes it a lot more difficult. Also in classroom demonstrations. By the way, it's even more instructive to do it with white light. All right, so let's come back to electrons. So what is the equivalent of a single wave or a single color laser with electrons? This means all the electrons. Remember the Broglie wavelength. Maybe I have it before. Yeah, here. Yeah. So let's see. Here's the Broglie wavelength, and this is MV. So this is basically the square root of the, apart from some factors, basically the square root of the kinetic energy, right? And so the kinetic energy, so then let's see, where's the kinetic energy? So the electrons emitted from this source are accelerated by a voltage in this direction, which I have omitted because it's not principally important for the thing. So the electrons are emitted and accelerated in this direction. And this acceleration lends the kinetic energy to the electrons. And the width of the energy packet of the electrons is very narrow. This means that the electrons emitted at a given high voltage from this electron source are very highly monochromatic. It's very similar to a laser with a single color. Yeah, and actually it's good that you asked this question again, because only this sort of monochromaticity of the electrons makes the observation of these nice fringes possible. If you would have an electron emitter which sends us slow and fast electrons or so, everything would be washed out again. Yeah, you wouldn't see anything, like with a white light source in a classic experiment. But here we can really make a very homogeneous velocity for the electron with a very narrow velocity spread, and this corresponds very well to the action of the white light. Yeah. Let me also go to the other experiment, to the neutron experiment. Let me briefly go to this Marthinda experiment. Well, here you have seen the real part. Now, again, I mentioned in my last slide is precision. And so what about the colors and the spectral properties of a Marthinda experiment? Again, if it is a laser beam, such as a laser pointer with a green beam or so, it's again dead easy. You just put all these things, align them roughly, and then here you have the fringes, yeah? And then when you move one of these mirrors in and out, you make one of the paths a bit longer, it doesn't matter. You see a very nice oscillation of the output ports from the left to the right and back and so on. Now, when you use white light, then you will see nice interference only when this optical path is exactly identical to this optical path. Okay, then it doesn't matter what the wavelength is. We call it zero phase interference. Yeah, and you will see very nice interference fringes here, and so even for a thermal beam, and this is why you can even use a thermal neutron beam, which has many different velocities of the beam, to see very nice fringes. Because the machining here is so exact that the optical path or the pathway for the neutrons in this direction and in this direction is perfectly identical and sufficient to see the interference fringes, which you do see here, yeah, as a function of introducing a slight delay here, or as a function of rotating the spin 1/2. Okay, I hope that gave you an idea of your question. Well, I don't see any other questions, but we had a very good question section already. So I wish you a good evening. It's now 5:30, 5:20 for you. For me, it's 6:20. I will have dinner now. I wish you a good evening. I hope to see you again. And I hope that you could get a little profit from my lecture. Thank you very much again, and hope to see you at some point. Bye-bye.
Thank you too, Prof. May God bless you.